Hi, I'm Dick Seitz. Welcome to the Software Screw-Up series. Today's episode is about benchmark programs and what they're actually measuring. I'm going to give 5 examples. Here's the first one. Which drink would you rather have? The tall one or the shorter, perhaps wider one? Our eye tends to favor height over width, so we might substitute measuring height for measuring volume. But both the glasses here are exactly the same volume. The point is, it's easy in performance work to end up measuring the wrong thing without realizing it. Here's a second example along the lines of pay me now or pay me later. Some implementations of calloc, allocating memory from the operating system, zeros the pages by spending some time writing zeros to them. If you then have a benchmark that reads the time, does some work, reads the time, and subtracts, the time you measure excludes the page zeroing time. The picture is from a Fram oil filter commercial from 1972, where the gentleman doing the repair work has this wonderful line in a wonderful voice that says, "Pay me now or pay me later." The link's on the next page here. If you have a different implementation of calloc that doesn't zero all the pages you allocate, but instead simply creates page table entries pointing to a kernel all zero page. When you read those pages, they read as 0. When you start writing them, you get page faults, which do a copy on write to allocate a real physical memory page and fill it with zeros and then return. If you read the time and do work that gets all the copy on write page faults and read the time and subtract, your end-to-end measurement includes the copy on write page zeroing time. So in this case, your measurement takes longer because you're paying later for the zeroing that was excluded in the first case. There's the URL of the Fram oil filter commercial if you want to look at it. Here's a third example. You could, in writing to disk, read the time, do a bunch of works that writes directly to disk through some mechanism that forces avoiding all the buffering that's usually there. In that case, your end-to-end measurement includes the actual disk transfer time. If instead you do what is more common, you end up writing to a RAM buffer, and then sometime afterwards, those writes eventually are written to disk by the operating system or the file system. In that case, if you read the time, do the work of the RAM buffer, and read the time and subtract, your end-to-end measurement excludes the actual disk transfer time, which can be quite substantial. And it's also then lying around as work debt or performance debt to be dealt with later. So here's our fourth example. Here's a simple end-to-end measurement where you read the time, you do some work, you read the time, subtract, and it appears that everything that you're measuring is what you intend to measure. But in fact, that work could have interrupts that you don't normally think about or you can't normally see very easily. And all the interrupt time gets charged to your end-to-end measurement. It includes the interrupt time. And so you end up paying for something that's not your work, but somebody else's work. Perhaps, in fact, somebody else's lazy disk writes, as in the previous example. Here's the fifth example about what are you really measuring. So usually in the pictures in our heads of what our programs are doing, there's some things missing, including cache misses. So here's a loop that goes through with stride of 8, going through a big array or whatever, and it uses all of the sets in the cache. And if the array size is appropriate, the whole thing fits in the cache. So you read the time, you do the loop, you read the time, you subtract, and you're not charged for any cache misses because all the data is in the cache. That's the simple picture in our heads. However, if your stride is, for instance, 4K, in most L1 caches, things that are spaced 4K apart will all fit in the same set in the cache, in a set associative cache. And instead of using all 64 sets in a typical L1 cache, you end up using only just one set, which only holds about maybe 4 or 8 or 16 cache lines. And so you get lots of cache misses going through a larger array. In that case, your end-to-end measurement includes the unexpected missed time, which isn't in the picture in our heads. So to summarize, when you're just doing the end-to-end timing without paying attention to what's going on within the timing, when you're blind to the internals, that can easily lead to measuring the wrong thing. Also, as we saw in the last example, when your code differs substantially from the hardware optimized case, everything fitting into just one cache line instead of spread across the whole cache, when that happens, your performance can fall off a cliff. And so, since all of our modern processors have all sorts of speed up mechanisms, you need to keep in mind that no good speed up goes unpunished. Thank you for listening. Come back and listen to another one.